Hello everyone, and welcome to this presentation on model training, optimization, and tuning with Amazon SageMaker. Machine learning has become a critical part of modern technology, helping organizations make smarter decisions through data. However, building an effective machine learning model involves more than simply feeding data into an algorithm. It requires proper training, careful optimization, and fine-tuning to achieve the best possible performance. In this presentation, we will explore how Amazon SageMaker simplifies these processes by providing powerful tools for building, training, optimizing, and deploying machine learning models efficiently. By the end, you will have a clear understanding of how SageMaker helps data scientists and developers create high-performing machine learning solutions. Now, let's understand what happens during model training. Model training is the process of teaching a machine learning algorithm to recognize patterns and relationships within data. Think of it as training a student for an exam. The more examples the student studies, the better they become at answering new questions. Similarly, a machine learning model learns from data so it can make accurate predictions on information it has never seen before. The process begins by providing input data to the algorithm. This data contains features, which are the pieces of information used to make predictions, and target values, which represents the correct answers. As the algorithm processes the data, it learns the relationship between the features and the target values. During this process, the model continuously adjusts its internal parameters to reduce errors and improve its prediction. To determine how well the model is learning, its performance is measured using evaluation matrices such as accuracy, precision, recall, or error rates. These matrices help identify whether the model is improving or if further adjustments are needed. The ultimate goal of model training is create a model that can accurately predict outcomes on new unseen data, making it useful for real-world application. Now, let us understand how model training works. Let's look at the role of Amazon SageMaker in the model development process. Amazon SageMaker is fully managed machine learning service provided by AWS, which supports the entire machine learning lifecycle from data preparation to model deployment. Instead of using multiple tools for different tasks, SageMaker brings everything together in a single platform, making model development faster and more efficient. The process begins with data preparation, where data sets are cleaned, organized, and transformed into a format suitable for machine learning. Once the data is ready, developers can build and design machine learning models using SageMaker's integrated tools and frameworks. After building the model, SageMaker provides powerful resources to train it on larger data sets. The platform automatically manages the underlying infrastructure, allowing developers to focus on improving the model rather than managing servers. To further enhance performance, SageMaker supports hyperparameter tuning, using automatically test different configuration to find the setting that produce the best results. It also enables experiments tracking, allowing teams to compare model versions, monitor performance, and documents and their findings. Finally, SageMaker simplifies model deployment by making it easy to launch trained model into production environment. It also provides tools to monitor deployed models and manage different model versions over time, ensuring that machine learning system remains accurate, reliable, and up to date. Overall, SageMaker serves as a computer end-to-end solution for building, training, optimizing, and deploying machine learning models. One of the biggest advantages of Amazon SageMaker is its collection of built-in machine learning algorithms. These pre-built algorithms allow developers and data scientists to quickly create models without having to design complex algorithms from scratch. Let's look for some examples. The first is linear learner, which is commonly used for classification and regression tasks. It helps predict outcomes such as whether an email is spam or estimate values like house prices. Another popular algorithm is XGBoost. It is known as for its high performance on structured or tabular data and is widely used in machine learning competitions and real-world business applications because of its accuracy and efficiency. SageMaker also supports LightGBM, a gradient boosting algorithm designed for speed and research efficiency. It can produce large data sets quickly while maintaining strong predictive performance. Finally, there is k-nearest neighbors or KNN. This algorithm makes predictions by comparing new data points to similar examples in the training dataset. It's commonly used for recommendation systems and pattern recognition tasks. This built-in algorithm offers several benefits. They reduce the need to develop algorithm from scratch, saving both time and effort. They are optimized for AWS infrastructure, ensuring efficient performance and scalability. They also support many common machine learning use cases and also allows team to experiment and prototype solutions much faster. Overall, SageMaker's built-in algorithm help organizations and accelerate model development while maintaining high performance and reliability. Now let's look at some common algorithm use cases and understand where each algorithm performs best. First is the linear learner. This algorithm is best suited for classification and regression problems. A common example is customer churn prediction, where businesses try to identify which customers are likely to stop using their services. Next is XGBoost, which is highly effective for tabular and structured data because of its strong predictive performance. It is widely used in industries such as finance and banking. A common use case is fraud detection, where the model analyzes transaction patterns to identify suspicious activity. Another powerful algorithm is LightGBM. Like XGBoost, it is a gradient boosting algorithm, but it is specifically optimized for speed and efficiency. It works particularly well with large structured data and is often used when organizations need fast training time while maintaining high accuracy. We also have k-nearest neighbors or KNN. This algorithm makes prediction based on the similarity between data points. One of its most common application is product recommendation system, while similar customer behaviors are used to suggest products that users may be interested in purchasing. Before we discuss optimization and tuning, it's important to understand some key training concepts that are commonly used in machine learning. The first concept is epoch. An epoch represents one complete pass through the entire training dataset. If a model is trained for multiple epochs, it means the model reviews the entire dataset multiple times to improve its learning. Next is the batch size. Instead of processing all data at once, the dataset is divided into smaller groups called batches. The batch size determines how many samples are processed before the model updates its parameter. The step refers to a single training update based on one batch of the data. Every time the model processes a batch and adjusts its parameters, one training step is completed. Another important term is the learning rate. The learning rate controls how much the model changes its internal parameters after each step. If the learning rate is too high, The model may learn too quickly and miss the best solution. If it's too low, training can become very slow. We also have the loss function, which measures how far the model predictions are from the actual answers. During training, the goal is to minimize this loss value because a lower loss generally indicates better model performance. Finally, optimization is the process of reducing the model's error by continuously adjusting its parameters. Optimization algorithm helps the model move towards the most accurate solution possible. Together, these concepts, epochs, batch size, steps, learning rate, loss function, and optimization, forms the foundation of machine learning training and a major role in determining how well a model performs. Now, let's discuss the most important concept in machine learning, the train-test split. The train-test split is used to evaluate how well a machine learning model can generalize to new unseen data. In other words, it helps us determine whether the model has truly learned patterns from the data or has simply memorized the training examples. The data set is typically divided into three parts. The first is the training set, which is used to teach the model and help it learn relationship between the data. This is the portion where the model sees during the training. The second is the validation set. This data set is used during development to tune hyperparameters, compare different models, and make improvements without affecting the final evaluation. The third is the test set. The test set remains completely unseen during training and tuning. It is used only at the end to measure the model's final performance and estimate how well it performs in real-world situations. This train-test split is important for several reasons. First, it prevents us from evaluating the model only on the data it has already seen. Second, it helps detect overfitting, which occurs when the model performs very well on training data but very poorly on new data. Third, it provides a realistic measure of performance on unseen data. Finally, it allows for a fair comparison between different models and configuration. By separating data into training, validation, and testing sets, we can build machine learning models that are more reliable, accurate, and capable of making predictions in the real-world application. After a model has been trained, a next step is inference. Inference is a process of using a trained machine learning model to make prediction on a new data. There are two common types of inference, real-time and batch inference. Let's start with the real-time inference. As the name suggests, real-time inference provides prediction immediately after the data is received. These systems are designed for lower latency, meaning they can respond within milliseconds or seconds. Real-time inference is commonly used in user-facing models where instant decisions are required. For example, when a customer makes an online purchase, a fraud detection model may analyze the transaction instantly and determine whether it appears suspicious before the payment is approved. In this case, a fast response is critical. On the other hand, batch interference is used when immediate predictions are not necessary. Instead of processing one request at a time, the model processes large group of records together. These jobs are often scheduled to run a specific interval such as daily, weekly, or monthly. A good example is a customer churn prediction. Rather than evaluating each customer individually in real time, a company may run a batch job once a week to identify customers who are likely to stop using their services. The main difference between these two approaches is speed and time. Real-time inference focuses on delivering immediate responses for interactive applications, while batch interference focuses on efficiently processing large amount of data when timing is less critical. Choosing between a real-time and batch inference depends on the business requirements, the volume of data being processed, and how quickly prediction needs to be delivered. Now, let's explore an important concept, which is the difference between parameters and hyperparameters. Although these terms sound similar, they serve very different purposes in the training process. Let's begin with parameters. Parameters are the values that the model learns automatically during the training. As a model processes data and makes prediction, it continuously adjusts these values to reduce errors and improve accuracy. A common example is weight in a neural network, which determine how much influence each input has on a final prediction. Then is the hyperparameter. They are not learned by model. Instead, they are set before training begins and controls how model learns. This setting influences the training process and can have a major impact on performance. Example includes the learning rate, which controls how quickly the model updates itself. The batch size, which determines how many samples are processed at once, and the settings such as number of trees or maximum depth in the algorithm like XGBoost. Understanding the difference between these two is very important. Parameters are learned automatically, while hyperparameters must be chosen and configured by the developer or data scientist. This is where tuning becomes valuable. By experimenting with different hyperparameter values, we can often improve a model's accuracy, efficiency, and overall performance. In fact, many machine learning projects spend significant time finding the optimal hyperparameter settings. In simple terms, parameters are what the model learns, while hyperparameters determine how the model learns. Now that we understand what hyperparameters are, let's explore the different methods used to find the best hyperparameter setting. Hyperparameter tuning is the process of searching for optimal combination of values that produces the best model performance. Since different settings are significantly affect accuracy and efficiency, choosing the right combination is the important step. One approach is manual training. In this method, the user changes hyperparameter values one at a time and compares the results. While this approach is simple, it can be time-consuming and may not always find the best solution. Another common method is grid search. It is systematically testing every possible combination of hyperparameter values within a predefined search space. Although it is thorough, it can become computationally expensive when many hyperparameters are involved. Then is the random search. It offers more efficient alternative. Instead of testing every combination, it randomly selects combination from the space search. Surprisingly, a random search often finds good results faster than grid search, especially when only a few hyperparameters have major impact on performance. A more advanced technique is Bayesian optimization. This method uses the result of previous training runs to intelligently choose the next set of hyperparameter to test. By learning from past experiment, it can find high-performing configuration using fewer training jobs. Amazon SageMaker simplifies this entire process to SageMaker Automatic Model Tuning. This feature automatically launches multiple training jobs, evaluates that performance using a selected objective metric, and searches for the best hyperparameter values. Instead of manually testing configurations, SageMaker performs the experimentation automatically and identifies the model that delivers the strongest results. By automating hyperparameter tuning, SageMaker helps data scientists save time, reduce computational effort, and build more accurate machine learning models. Cross-validation. Cross-validation gives a more reliable estimate of model performance. Here it is how it works. The data set is divided into several smaller groups called folds. The model is trained using some of these folds and then validated on a different fold. This process is repeated multiple times with a different fold being used for validation during each round. After all the rounds are completed, the results are averaged to produce a final performance estimate. This gives a more balanced and dependable evaluation because the model is tested on different subsets of data rather than just one. It is especially useful when the dataset is small and limited, since it allows every data point to contribute to both training and validation at different stages. Finally, cross-validation helps detect unstable model performance by revealing whether results vary significantly across different folds. Overall, cross-validation provides a more trustworthy measure of model performance and helps data scientists make different decisions when selecting and tuning machine learning models. Now is overfitting and underfitting. The goal of machine learning model is to learn patterns from training data and applying that knowledge to new unseen data. However, models can sometimes learn too much or too little, leading to poor performance. Overfitting occurs when a model learns the training data too closely, including noise and random variations that are not actually important. As a result, the model performs extremely well on the training data but struggles when presented with new data. For example, imagine a student who memorizes every question and answer for a practice test instead of understanding the concepts. This may score perfectly on the practice test but perform poorly when faced with different questions on the real exam. That's exactly what happens with an overfitted model. On the other hand, underfitting occurs when a model is too simple to capture the underlying patterns in the data. In this case, the model performs poorly on both training data and test data because it has not learned enough information to make accurate predictions. Using the student analogy, again, underfitting is like a student who barely studies before the exam. Since they haven't learned the material properly, they struggle on both practice exams and the final exams. The ultimate goal is to find a balance between these two extremes. We want a model that learns the important patterns in data without memorizing unnecessary details. Such a model is said to be generalized well, meaning it performs accurately on both training and new data or unseen data. Achieving this balance is one of the key objectives of model training, optimization, and hyperparameter tuning. Then is the SageMaker Experiments. It becomes extremely valuable, and it is a feature that helps data scientists organize, track, and compare machine learning training runs. Instead of manually recording results in spreadsheets or notes, SageMaker automatically stores important information from each experiment. Some of the key items that can be tracked, including datasets version, algorithm choice, hyperparameter values, training job results, evaluation matrices, and model artifacts. For example, imagine training multiple versions of a model using different algorithms. Without proper tracking, it can be difficult to remember which configuration produced the best result. SageMaker Experiment solves this problem by maintaining a complete history of each training run. This capability offers several benefits. It keeps experimentation organized, it makes it easier to compare to different model versions, and it identifies the most effective approach. It also supports repeatability, allowing teams to recreate successful experiments using the same setting and data. Finally, it improves collaboration because team members can access and review experiments details without relying on personal notes. Then is the SageMaker Debugger. It is a tool designed to monitor and analyze the training process in the real time. It helps data scientists detect issues early, understand model behavior, and improve overall performance. One of the key things is loss values. Since the loss function measures prediction error, tracking loss helps determine whether the model is learning effectively or if training has stalled. In addition, the tool tracks weight and tensors, providing insights into how the model internal parameter change throughout the training process. This allows developers to better understand what is happening inside the model. The importance of SageMaker Debugger lies in its ability to detect problem early. Instead of discovering issues after training is complete, developers can identify and address while training is still running or not. This improves troubleshooting, increases visibility into model behavior, and leads to more efficient training workflows. Overall, SageMaker Debugger provides valuable insights that help machine learning teams build more reliable models while reducing the time and effort required to diagnose training issues. Then is the Model Registry. The Model Registry is a centralized repository that helps organizations store, manage, and track machine learning models throughout their lifetime. It serves as a system for organizing model versions and controlling which models are ready for deployment. One of its primary functions is to store model version. Every time a model is trained or updated, a new version can be registered, making it easy to track changes over time. Another key feature is support for approval workflows. This capability helps organizations organize model before deployment and support governance in machine learning workflow. It may begin in a pending approval stage while being reviewed. If it meets performance and quality requirement, it is marked as approved and becomes eligible for deployment. If the model fails to meet the expectations, it can be marked as rejected and prevented from entering production. Overall, SageMaker Model Registry provides a structured way to manage machine learning models, ensuring that the right versions are tracked, reviewed, and deployed with confidence. Now, let us discuss about a powerful technique used to improve performance, which is called model assembling. Model assembling is the process of combining multiple machine learning models to produce better prediction than a single model alone. The idea is simple. Instead of relying on model's precision, we combine the strength of several models to achieve more accurate and reliable results. The first is bagging, short for bootstrap aggregating. In this approach, multiple models are trained independently on different samples of the data. Their predictions are then combined, often through averaging or voting. A well-known example of bagging is the random forest algorithm. Then is boosting. Unlike bagging, boosting trains models sequentially. Each new model focuses on correcting the mistakes made by the previous model. The third is stacking. In stacking, multiple models make prediction and then another model called meta model learns how to combine those predictions to generate a final result. This approach leverages the strength of different algorithms simultaneously. Model assembling offers several important benefits. First, it can significantly improve prediction accuracy by combining insights from multiple models. Second, it reduces the weaknesses of individual models because error made by one model can be compensated by other. In many cases, assemble method outperform single models, making them a popular choice in machine learning competitions and real-world application. They are especially useful for complex prediction problems where achieving high accuracy is critical. Overall, model assembling is a powerful strategy that helps create more robust, accurate, and reliable machine learning systems. In summary, model training is the process of teaching algorithm to learn patterns from data. SageMaker supports training, tuning, debugging, experiment training, and model version management. Train and test split and cross-validation helps evaluate model fairly. Hyperparameter tuning improves performance while model registry helps manage model before deployment. This will be all for my today's video. I will see you in the next video. Until then, take care and bye. If you have any doubt in this video, feel free to comment in the video and ask the question. Thank you so much.